Hello everyone, welcome to the material science class. This is the third video of chapter 2. In this chapter we are discussing the atomic structure or the structure of atoms and the different types of forces that would be located at the atomic scale. So over the previous two videos we have discussed the atom, the structure of the atom, we discussed the element, the difference between the atom and the element, compound, mixture, the atomic number, the atomic mass and the atomic weight. And we know how we can calculate these three quantities for any molecule or atom. Also, we discussed the different forces that would be located wherever inside the atom, which are the electromagnetic force, the weak force, the strong force, and the gravity force. In the meanwhile, in the second video, we focus more on the intramolecular forces. And the intramolecular forces are bonding time force, that the objective of this force is to bond, to collect atoms together, molecules together to form a material. And we mentioned that in many of the cases, these intramolecular forces are generated between two atoms. And the objective again of this force is just to collect and bond and form a material. These forces that we have discussed over the second video are the ionic force, or commonly known as the ionic bonding or the ionic bonding force, the covalent, and the metallic force. Also, we discussed the different general properties of solid that would be made of any one of these types of forces or bonding forces. Now, the objective of our third video is to discuss the intermolecular forces. This intermolecular forces is the third group. We said that we do have three types of groups of forces. One of them, which are the electromagnetic force, strong, weak, and gravity force. These are the forces that are located inside the atom. And we discussed the intramolecular forces or the bonding force. We still have the third group that will be covered over this video, which are the intermolecular forces. All right, intermolecular forces are non-bonding forces between atoms or molecules. So again, if you remember from the previous videos, we said that there are some type of forces that could be generated between atoms. This common type of forces is the bonding force. If you do have two atoms that form a material, definitely there is a bonding force between them. But in addition to this bonding force, there is another non-bonding force, which is the intermolecular forces. So the intermolecular forces, it is like forever force that exists between any two things, between any two atoms, between any two molecules, between an atom and another molecule. So there is intermolecular forces do exist there. So generally speaking, intermolecular forces are forces that generate between any two objects, whatever atoms or molecules inside the material. Make sense? But the objective of this force is non-bonding. It means that there is no tendency of this force, or this force is weak, or is inapplicable to bond atoms or molecules together to form a material. These are non-bonding forces. But over the previous video, we have discussed the bonding forces like ionic, covalent, and metallic forces. The tendency of that forces is to collect, is to form a material. So that's why they are very strong force. They are commonly known as the bonding force. But these type of forces are non-bonding forces. This is what we are going to discuss over this video. So the intermolecular forces are non-bonding forces that would generate between atoms and molecules. And remember that if you have two atoms and there is a bonding force between them, in addition to this force, there is another force, which is the intermolecular force that do exist in parallel with the bonding force. But the contribution of this non-bonding force of the intermolecular forces is very weak in comparison to the bonding force itself. So that's why it is very negligible, and many of people don't care about the existence of these intermolecular forces between atoms. But they do exist. This is something that you should understand, that this intermolecular forces do exist between atoms as there is bonding force, but they are weaker. So they are weak compared to the intermolecular forces or the bonding force. Intermolecular forces are also called as van der Waals forces, which are commonly known by this name. So these van der Waals forces, it is like a group of force. It is not just one type of force. It is a list of forces that could be generated between two different objects, or two objects like two atoms, two molecules, or even between atom and molecule, as we mentioned. Types of the intermolecular forces or the non-bonding forces are London Dispersion Forces, also known as induced dipole interaction. You have to acknowledge and understand the two terms. So this is the London Dispersion Force or the induced dipole interactions. So we're going to talk a little bit the interaction through this video. Also the dipole, there is another type which is dipole, induced dipole interactions, and there is dipole interactions, and there is hydrogen bonding interactions. So it is highly, from this list, there are some points that you should understand here. First of all, that the weakest of these four forces is the London Dispersion Forces. This is the weakest of them all. And the strongest one is the hydrogen bonding interaction. So this is the weakest of these four forces, and the hydrogen bonding is the strongest of these four forces. This is one thing. The Dybole-induced dipole interaction, it is stronger than the London Dispersion Forces, but weaker than the Dybole-Dipole interactions in many of the cases. The Diable-Dipole interaction, it is stronger than the Dybole-induced dipole interactions, but in many of the cases, it is kind of something also that you should understand, that the hydrogen bonding interaction, it is already Diable-Dipole interaction, as it will be explained. But since we do have hydrogen, this is like a special form of the Diable-Dipole interaction, which in many of the cases is the strongest form of the Diable-Dipole interaction, as it will be explained over the next slides. All right, another thing that you should understand is that there is a difference between dipole and induced dipole. As you can see, like London Dispersion Force, it is induced dipole interactions. So there is like a compound word, induced dipole. This is one type of interaction, kind of. And we do have Diable, which is another thing. So there is a difference between the dipole or the permanent dipole and the induced dipole. You should acknowledge this difference, as it will be explained over the next slide. So that's why we do have here induced dipole interactions, and we do have dipole and induced dipole. So this is like two parts, two different things. There is dipole, which is a permanent dipole moment, and we do have induced dipole. So these two different things. So this, between dipole and induced dipole, there could be some type of interaction which would be another form of the intermolecular forces, or we may have a force or interaction that generates between two permanent dipoles. So dipole and dipole, it means permanent dipole moment and another permanent dipole moment. These dipole moments will be explained over the next slides. Make sense? So this, first of all, but the thing that you should acknowledge so far is that we do have four different types of intermolecular forces. In general, there are only three. There is induced dipole, and there is dipole, induced dipole, and there is two dipoles, like Diable-Dipole interaction. The hydrogen bonding interaction, it is a special type of the Diable-Dipole interaction. So something also that you should understand, that the hydrogen bonding interaction, it is Diable-Dipole interaction. Make sense? So these are the different types of the intermolecular forces, and again, they are weaker than the intramolecular forces. So that's why the tendency of these forces are non-bonding, and they do generate between any two objects, whatever atoms, molecules, or atom and molecule. Make sense? So they are forever that forces that exist in between any two objects inside the material. So let us start with the London Dispersion Force, which is the weakest of these four. So the London Dispersion Force, which is also known as the Induced Dipole Interactions Force or interactions, all molecules or all atoms interact with each other through London Dispersion Force. So this force exists between all molecules, whatever their type, their polarity, no matter what these molecules are, there is London Dispersion Force between them, or two atoms, there is London Dispersion Forces between them. Make sense? Or the induced dipole interaction, which is the London Dispersion Force. So to understand this thing, let us define two different types of molecules or objects or atoms, kind of. But let us focus on the molecules for now. We may have a molecule that is polar, and we do have a molecule, another molecule that is non-polar. So we do have polar molecule, non-polar molecule. The polar molecule, it means that it carries a charge in a certain direction, or it is non-symmetric molecule. So what does it mean, non-symmetric molecule? It means that the right side for the molecule, for example, may have a positive charge over higher than the negative charges over the other side of the molecule. So we're going to say that there is non-symmetry in that molecule. that one side is more positive than the other side. So we're going to have here positive charge, more positive charges over the right side, for example, and over the left side, we're going to have more negative charge. It works like the magnet. We'd have two sides of the magnet, we'd have the north and the south. So this is like the positive and negative sides of this molecule. So in that case, this molecule is non-symmetric in terms of polarity, is non-symmetric in terms of electricity, in terms of charges. So this type of molecule is commonly known as polar molecule. But the non-polar molecule is the symmetric molecule. It means that if you measure the charge, it will be equivalent, it will be the same all the way around over all direction, over all sides of that molecule. So we're going to say that this is non-polar molecule. Make sense? The polar molecule that is non-symmetric, that has positive and negative, it carries a permanent Diable moment. This Diable moment, this is like kind of force. This is like kind of moment that would bring this molecule to be in an interaction with another molecule of the opposite charge. So there would be some interaction forces that would be generated for that molecule because of the difference in the charges. It's going to be much more clear when we discuss the second type, which is the Dipole-Induced Dipole Interaction. But for now, let us distinguish that we do have two types of molecules. One is polar, the other one is non-polar. The polar molecule, it is non-symmetric in terms of charges. You're going to find one side more positive or more negative than the other side. But the symmetric one, that the charges are equivalent all around the molecule, this is electrically symmetric molecule, is known as non-polar molecule. Make sense? So let us consider this example of two non-polar molecules. Assume that we do have two non-polar molecules, molecule 1 and there is molecule 2. Molecule 1 is made of 3 atoms. So these circles, these things are 3 atoms of the same type or 2 different types. No, it doesn't matter. Like assume you'd have a molecule that consists of 3 atoms, and we'd have another molecule that consists of 2 atoms. And these 2 molecules are non-polar. So what does it mean non-polar? It means that they are electrically symmetric. So what does it mean electrically symmetric? If we're going to consider this atom, the atom, it is electrically symmetric. Why? When we discussed the structure of the atom, we said that the atom has a nucleus, and the nucleus contains protons and neutrons. The neutrons are neutral in terms of electricity, but the protons, they do have positive charges, and this is the nucleus. So this makes the nucleus, which is the core of this atom, is of a positive charge because of the proton there, right? Makes sense. But how about the electron? There are some electrons surrounding this nucleus, rotating in their definite orbits around the nucleus, and electrons, as we mentioned, they are carrying a negative charge. And the number of the electrons should be equal or equivalent to the number of the protons inside the nucleus. It means that the positive and negative charge, they kind of equivalent for the atom. So that's why the atom itself, in the ideal case, it should be neutral, has 0 charge, or there is no dipole thing for that atom in the ideal case. So as you can see, the ideal form of that atom, that you're gonna find the nucleus that located inside the core with a positive charge, and the electrons surrounded by a negative charge due to the electron. So you're gonna see like you do have positive charge that is surrounded by a cloud of negative charges of that due to the electron that's rotating in their orbits around the nucleus. Make sense? So this is what's happening for all of these atoms. So this is one atom and another atom, another atom. It has its own positive and negative charge, positive and negative charge, and so on. And all of them, they are bonded together by another type of force, which would be ionic, covalent, or metallic, that combine these 3 atoms together to form one molecule. So the type of force between these atoms, it is bonding force, which is not intermolecular forces. There should be some intermolecular forces between atoms, yes, but it is very negligible in comparison to the bonding force. But now we are discussing the intermolecular force between the molecules themselves. So there is one molecule here that consists of 3 atoms, and this molecule consists of 2 atoms, and everything is symmetric in terms of electricity. So what does it mean? For example, if we choose this side of this molecule, it will have a negative charge that is equivalent to the other side. This side has a negative charge that is equivalent to this side, and so on. So there is kind of symmetry in the electricity or the charges all around this molecule. The same thing for the other molecule. So we're gonna say that these two molecules are nonpolar molecules. They are carrying zero dipole moment. There is no dipole moment. It means that there is no non-symmetry in the polarity or the electricity around this molecule. They are electrically symmetric. This is for these two molecules. So in case that, assume that we do have these two molecules, and for some reason these two molecules, they're gonna collide to each other. They're gonna hit each other. So molecules in general inside the material, they are all the time under motion. They are vibrating about their equilibrium position and moving. All the time they are under continuous motion inside the material. This is because of the external forces or external stimulus like force, heat, vibration, whatever. Anyway, these molecules all the time, they are under continuous motion. While these two molecules are moving inside the material very close to each other, they would collide to each other, or they would hit each other, or at least they're gonna come very close to each other. So what's gonna happen in that case? This will make one of the charges, like we do have a negative charge here, and there is a negative charge over this side. So when the negative comes very close to the negative, they're gonna repel each other. They're gonna push each other apart. This is gonna make the nucleus like kind of shifted toward the side to collect more, to attract the negative charge. Because for example, you do have some electrons here over this side. If we just choose this side, and this side there are some electrons here, right? When these two molecules come close to each other, the negative charge will be repulsive to the other negative charge of the other molecule. So this side is negative of this molecule, and this side is negative. When they're gonna come close to each other, these two negative things will repel each other. Make sense? So this is gonna enforce some of the electrons, whatever of this molecule or that molecule, to move to the other side. So if we assume that these electrons of these atoms, this atom and this atom, for example, they're gonna move to the other side. They're gonna push or repel on the other side. So this nucleus will become non-symmetric. Like there is negative charge, so many negative charge over the other side, but there is no negative charges in this side. So what's gonna happen for this nucleus? It will start to attract the electrons of the other molecule, and this what generate this type of London dispersion force. This force, it should be generated between two different charges, positive and negative. But in the ideal case, while these two molecules are apart from each other, there is no forces in that case. The force is zero almost. Unless they're gonna come very close to each other or even hit or collide to each other. So what's gonna happen, as I mentioned, these electrons over this side will be pushed, will be repelled on the other side, where they're gonna move to the other side, back beyond or behind the nucleus itself, because of the similarity in the charges with the electrons of the negative charge of the other molecule. This is gonna make this nucleus have a negative charge over this side more than this side. So this will enforce the nucleus to attract the electrons of the negative charge of the other molecule, and this what generate the London dispersion forces. So molecules 1 and 2 are electrically symmetrical in the ideal case, as long as they are apart from each other. Due to molecules' motion, molecule 1 may collide with the molecule 2. Upon this collision, excites the electrons cloud. There is electron cloud here around all of these atoms of the two molecules to repel each other. So there are some electrons here, we repel the other electron on the other side of the molecule, causing a displacement of some electron density away from the nucleus. The density of the electron here will decrease, and it became more dense. More electrons will be located over, beyond, or behind this nucleus, hiding from the repulsive force that comes from the other electron. Make sense? And this is what already represented here in this figure. So as you can see, these electrons, so if you consider just the thickness of this electron cloud here, it became very thin. and more it became very thicker on the other side. It means that more electrons had been moved on the back, beyond or behind the nucleus itself, and this make this side more positive than this side. This became more negative, this became more positive, so the positive will attract the negative of the other molecule. So remember that this is molecule 2 and this is molecule 1. Make sense? So this is how this type of force is generated. So the nucleus is then poorly shielded by its own electrons and attracts the electron cloud of the other molecule. As we mentioned, it becomes more positive here, so it will attract the negative of the other molecule. And by the way, the same is happening for the other atom. So this is what happened for this atom, that this electron moved back, and the same thing is going to happen to the other electrons. They're gonna move behind the nucleus, so this is gonna make this side more negative, and the positive is becomes here. This side will be more positive and the negative will be here. So you're going to have positive, negative, and positive, negative on the other side. So these two molecules or these two atoms will be attracting each other, making the two molecules attracted together through this London Dispersion Force. This results in a small Diable Moment. So what is the Diable Moment? Diable Moment, which is this one. Let us just talk about these two atoms. These two atoms, when they are combined together, or just one atom, let us choose one atom. So as you can see, this side became more positive and this side became more negative. So this will result in something that we call as Diable Moment. Diable Moment, it means that you're gonna have non-symmetry of this particle or this object or this atom or molecule. So here we are talking about just this atom. This atom has a positive side more than the negative side. So there is direction. Usually we define the direction of this Diable Moment that it comes from the positive going to the negative side. So there is kind of moment that would make this atom rotate and shift to be attracted in equilibrium with another atom, and this is what's happening here. So there is like kind of attraction between the positive to the negative of the other atom. So there is Diable Moment that has been generated over this atom, and there is another Diable Moment that has been generated over this atom. This is what makes these atoms attracted together. So this Diable Moment is something that needed to bring an object in an interaction with another object of different charge, depending on the difference in the charges. So in the ideal case, this atom, all of these 5 atoms, they are symmetric. They have 0 Diable Moments. The same thing for the molecule themselves. They do have 0 Diable Moments. But upon the collision, what's happening? These negative charges will repel the other negative charges. This will result in instantaneous, just for one instant of time, a Diable Moment. For the instant that these two molecules are hitting or colliding to each other, there is an instantaneous Diable Moment that is going to generate, not a permanent one, just temporary thing that is going to generate. This is what makes these two molecules attracted to each other. If this collision, for example, is high, so they're gonna rebound again, right? Upon the rebounding motion of these two molecules, so this interaction force or this dipole will be eliminated or will be removed, and in that case these London dispersion forces will be 0 as long as the distance between the two molecules are increasing. But when they're gonna come very close to each other or collide to each other, this Diable Moment is going to generate again, and this type of force will be generated between the two molecules. So that's why it is instantaneous. Depends on as long as these two molecules come or hit to each other. Make sense? So this results in a small, and this Diable Moment is very weak. So that's why this force, it is a very weak force in comparison to the other intermolecular forces. This results in a small Diable Moment which generates an attraction force between positive and negative, between the positive side of the molecule and the negative side of the other molecule. So simply this is how the London Dispersion Forces is generated, or the operating principle of this type of induced dipole interactions. Make sense? Another thing is why we got the name induced dipole. Induced dipole, it means that this dipole to be generated, it requires something to enforce the molecule to generate this dipole. It means that this dipole is non-natural. It is not inherited into the property of this molecule. This molecule is non-polar, has zero. By default, this molecule by itself has zero dipole. There is no dipole there. There is no dipole moment. It is non-polar. But upon the collision or heading to each other, this dipole will be generated. So that's why it is induced. Requires something to create it, something to generate it. So that's why we got the name induced dipole. So induced dipole, it means that this dipole, it is not by nature. It is not permanent. It is instantaneous dipole that is happening upon collision or the two molecules come to very close to each other. Make sense? So that's why the London Dispersion Forces, we could give it a name as induced dipole interactions. So this is the first type of the intermolecular forces, again, that generate between any two molecules, something that you should understand that is going to be much more clear as we move on through the next slides, that this London Dispersion Force exists and generated between any two molecules, whatever they are, polar or non-polar. But for now, just to understand how it works, assume that we do have two non-polar molecules. There is no permanent dipole there. And they're gonna hit or collide to each other. So there is induced dipole that is going to generate. It is too small, yes, but it is sufficient to generate this type of force, which is the London dispersion forces between the two molecules. And again, it is instantaneous, so that's why it is induced upon the collision. Make sense? The second type of the intermolecular forces is dipole and induced dipole interaction. It means that we have two objects. One object has a permanent dipole, and the second object has an instantaneous dipole, or has no dipole by nature, but it would create Diable moment or generate Diable moment upon collision, which is typically happening if we do have two molecules. This is molecule 1 and this is the second molecule. Assume that. So the first molecule, it is polar molecule. Polar, it means that it has a permanent dipole. So this interaction, which is induced dipole interaction, it generates between a molecule with a permanent dipole. The molecule with a permanent dipole moment is called polar molecule. That collides with a molecule without a permanent molecular dipole or has no dipole is known as non-polar molecule. So this is non-polar molecule. Non-polar molecule. The non-polar molecule is symmetric. The charges is symmetric all around the boundary of that molecule. So it is surrounded by negative charges from all sides. The negative charge here is equivalent to the negative charge there, equivalent here to the top. All direction it has symmetry in terms of the electricity. But this one, it is polar. So what does it mean polar? It has embedded permanent dipole by nature embedded inside this molecule itself. Why? This side of this molecule is a positive and this is the negative side. So there is no non-symmetry here. There is no symmetry. It is non-symmetric. There is side that is more positive than the other side. There is side that is more negative than the other side. Which is a typical example of this case is hydrogen cyanide, which is the hydrogen atom is a positive, has a positive charge, and there is carbon and nitrogen. So the nitrogen, this makes this side more negative than the other side, or this side more positive than the other side. So that's why we're going to say that this is polar molecule with a permanent dipole that is already there. Make sense? So when this molecule comes very close to the other molecule, even there is no need to collide to each other. But although this is going to happen as long as these two molecules are all the time under motion, so when this molecule comes very close to the other molecule, so the negative side will reveal the negative side of this non-polar. Non-polar is surrounded by electrons. All around the molecule itself, from all directions, there are negative charges. They are symmetric, yes, but they are negatives. So the negative of this molecule will reveal the negative electrons of the non-polar molecule, pushing them away. So when these molecules are pushed away, what's happened? These electrons when these electrons are pushed away, they're gonna move behind the nucleus, making this nucleus unshielded by enough number of electrons, or not shielded by enough number of negative charges, so it will start to attract the negative charge of the other molecule. And this what generate this type of interaction. This type of interaction force, it is stronger somehow than the London Dispersion Forces, because here there is no polarity, there is no permanent dipole that exists, but because of the existence of a permanent dipole, this makes this type of force a little bit stronger than the previous type, which is the induced dipole interaction. So in the dipole-induced dipole, so we do have dipole which is permanent, and this molecule has no dipole moment, but it will induce a dipole moment. It will generate a dipole moment upon the collision with the other molecule. So how it works? So the collision itself causes a dipole to appear between by changes in electron density within the molecule. So how it works? For example, if we consider the HCN is a molecule with a permanent dipole, as I mentioned. How we represent this permanent dipole, as I explained before, this side is a positive side, and it is directed this direction. So this arrow indicates the direction of the negative. Like we do have positive going toward the negative side of this molecule. The nitrogen atom is electron rich. It means that it has more electron than the hydrogen side. So that's why this is the hydrogen. It has only one electron, which will be shared with the carbon through a covalent bond, as it will be explained over the next slides, making this one has only positive charge. One charge positive, and that's it. So it is completely positive here. There is no negative over this side, but the nitrogen has more electron. This is what makes the nitrogen side more negative than the other side. Is electron rich, and the molecular dipole points to the direction of this atom. So this is the direction of the dipole moment, directed into this or going in that direction toward the negative side, as I mentioned. Upon collision, the electron cloud of the second atom is revealed by the second atom, or the second molecule is revealed by the excess electron density on hydrogen or nitrogen. So there are lots of electrons here, and there are some other electrons. So this electron will be revealed moving behind, as I mentioned, the nucleus, making the nucleus like at the boundary positive, that it will be attracted to the negative of the negative charges of the electron of the nitrogen atom. So the positively charged nucleus becomes closer to the nitrogen atom and is attracted to it through the difference in the charges between the positive, this side is positive, negative, and this side is positive, so they're gonna attract each other. So this is simply how this type of dipole-induced dipole interaction is generated. So what is the difference between this type of interaction and the previous one? The previous one is generated for now, between two non-polar molecules. Just for now, it generates between two non-polar molecules. And in order to be generated, this requires the collision of two molecules together. This makes the electron cloud of one molecule reveal the other electron cloud of the other molecule, and this makes one of the sides, two sides, the side of this molecule and the side of this became like negative, and the other one became positive, so they can attract each other. Here, it happening the same way. Upon collision, the negative charge will push the other negative charge, making this side more positive to be attracted to the negative to generate this type of dipole-induced dipole interaction. So that's why we got the name dipole here. It means that there is one of the molecule that has permanent dipole, which is known as polar molecule, but the other one is non-polar. It means that it has no, under the ideal case, has no dipole moment. But upon the collision, there is an instantaneous dipole moment that is going to generate. Make sense? So these are these two types. The next type is Diable-Dipole interaction. Diable-Dipole interaction, now we can understand it. So simply this is going to be generated between two polar molecules. You can have one molecule that has a permanent dipole moment, and you have another molecule that also has a permanent dipole moment. Then these two molecules, they're gonna come close to each other or collide to each other to form this type of interaction between them. They won't gonna form a material or molecule, but instead there is a Dipole-Dipole interaction force that is going to generate between them. So this interaction generates between two polar molecules. Polar molecules are the ones with permanent dipoles. So this one has a permanent dipole directed in this direction. It means that the hydrogen is the positive charge and the negative charge going in this direction. So this side more negative than this side. And here it is directed up in that direction. It means that this is the positive side and this is the negative side. So when we do have two molecules of this polar molecule, two particles or two molecules of this type of molecule, and we do have only one molecule here, they're gonna be in a chemical interaction. This will generate a Diable-Dipole interaction, another compound that governed by the Diable-Dipole interaction between these three molecules. So we have one molecule, which is this one, that is its Diable moment directed in this direction, that will be in interaction with the other one. So as you can see, for example, the Br here, this side is negative, the hydrogen is the positive side. All the time the hydrogen has, this is what makes the hydrogen special, because the hydrogen has only one electron which will be shared with any other atom, making the atom, the hydrogen atom itself, to be completely positive. So we do have a positive for the hydrogen. This side, this is positive, this is also as well it is negative. Definitely this makes this side more negative charged. So we do have a negative charge that will be attracted to the positive, and positive will be attracted to the negative, or the negative to the positive. So this will create this Diable-Dipole interaction. So the Diable-Dipole interaction, it works very similar to the other types, but it generates between two polar molecules. Make sense? So the molecular dipole vector points towards high electron density. As I mentioned, this more negative, this is the direction of the more negative. There is an important notice here that polar molecules are also interact with each other through London Dispersion Forces. The dipolar interactions add to this force. So I'm just gonna explain this point. But what we discussed here, three types. The first one, which is the London Dispersion Forces. We said that this type of force will generate upon the collision between these two particles, or at least come very, very close to each other till they just touch each other, so they will induce some instantaneous Diable moment, right? So going back again to this example of the Diable-Dipole interaction, do you think that these two molecules are required to collide to each other to generate this Diable-Dipole interaction? It is not needed. When these two molecules are come close to each other, since they already have permanent dipole there is no need to induce dipole, to produce another dipole. You got my point? Like, you have one molecule that has side that is negative more than the other side, the same thing for the other molecule. So when these two molecules come to each other, this will start to rotate, the other one will start to rotate. If the positive of this molecule comes close to the negative of that molecule, they're gonna attract each other through Diable-Dipole interaction. But how about if the other option, the other way around? How about if the negative of this molecule comes close to the negative of that molecule? There is no interaction here, but instead the electron cloud of this molecule will be moved behind the nucleus, and the same thing for the other one, and this will generate also another interaction, but which is very similar to the London Dispersion interaction. So again, just to understand it, here what makes this molecule attracted to this one? Nothing, except unless they gonna hit or collide to each other. When these two molecules collide to each other, what's happened? The negative of this one will be moved behind the nucleus. The negative of this atom will be moved behind the nucleus. This makes one side positive, the other side of the other molecule will be negative, attracted together to induce dipole moment, which is instantaneous. But this requires collision together or coming very close to each other. Make sense? The condition for this thing to happen, that you should have a negative and a negative side of the other molecule, right? But how about this case? We said that we have two molecules. One is polar, the second one also is polar. This has positive and negative, positive and negative. If the positive comes close to the negative, they can attract each other through dipole-dipole interaction. But for some reason, if this molecule has been oriented in that direction to be the negative, very close to the negative of the other molecule, there is no dipole-dipole interaction that is going to generate. The dipole-dipole requires this positive to be attracted to the negative side. But now we do have two negative sides. So the two negative sides, they're gonna push the electron clouds behind their nucleus, making one side here positive, one side negative, and they're gonna attract to each other again, but through induced dipole. So there is another dipole that would be generated between these two polar molecules, but it will be instantaneous, that would generate a London dispersion force. So we can conclude from this that the London dispersion force also exists between these two types of molecules. If you have two polar molecules, definitely there is dipole-dipole interactions, but also there is induced dipole interaction that is going to generate between these two molecules. It means that the London dispersion force also exists there. You got it? Also, another interesting thing, also, if you understand that the London dispersion force, which is induced dipole interaction, is generated, it means that the dipole-induced dipole interaction also would generate between two polar molecules. So again, generally speaking, if you have two polar molecules, how many types of forces that could be generated between them? Three forces. The first one, by definition, is dipole-dipole interaction, which is the strongest of them, of the three forces. Why? This is polar, this is polar, this has a permanent dipole moment, this has a permanent dipole moment. When the positive side of this molecule comes close to the negative side of this molecule, they're gonna be attracted through dipole-dipole interaction. This is one option. Another option is that you do have the two molecules. The negative side of this one comes close to the negative side of this one, and they're gonna generate induced dipole, instantaneous dipole for just a while. So this will generate induced dipole between two negative sides of the two molecules. So you're gonna end up with an induced dipole, which is London dispersion forces. But how about this third force, Diable-induced dipole interaction? How could this third force be generated? This would be generated usually, as we discussed here. You should have like one of the dipole, you have a permanent dipole that it will be attracted to an induced dipole. So that's why we got the name Diable-induced dipole interaction. So going back to these two permanent dipoles, we said that one molecules could be oriented with respect to the other one to make the two negative sides come close to each other. And they, upon the collision, there will be induced dipole will be generated into this, in addition to the permanent dipole. Like in this molecule, it has already a permanent dipole, but because of the collision with the negative side of the other molecule, there would be induced dipole generated inside this one. And there is another induced dipole will be generated inside the second one, right? Temporary dipoles will be generated in this one and this one. When this temporary or instantaneous dipole is going to generate, if it for some reason it interacted with the permanent dipole of the other polar molecule, this will induce Diable-induced dipole interaction. Dipole here, it means the first dipole word. This word indicate a permanent dipole that interacts with induced dipole. So this would happen also here. Like this one will, in that case, upon the collision, this molecule has two dipoles. One is permanent, one is induced. This one will has two dipoles. One is permanent, one is induced. So if the two induced dipoles, the induced dipole of this one will interact with the induced dipole of this one, this gives the London dispersion force. If the permanent dipole and the permanent dipole of this one will interact to each other, so this will give permanent dipole or dipole-dipole interaction, which is the third force. But if the induced dipole of this one will interact with the permanent dipole of that one, this will give the second type, which is Diable-induced dipole interaction. So that's why we said that in general, if you do have two polar molecules, there are three forces of interaction that is going to generate between them, these forces are the London Dispersion Force, which exists between any molecule, whatever they are, and the Dipole-Induced Dipole Interaction and the Diable-Dipole Interaction. Make sense? But in case that you do have, so going back again to this one, this Diable-Induced Dipole Interaction generates between polar and non-polar. How about if you do have a polar molecule and non-polar molecule? The non-polar molecule will carry induced dipole, instantaneous dipole. But this one has a permanent dipole and induced dipole as well. Because when the negative comes close to the negative, there is definitely some induced dipole that is going to generate as well in addition to the permanent dipole there. So generally speaking, any polar, what distinguishes a polar molecule from non-polar molecule? The polar molecule can carry two types of dipoles. One is induced upon the collision. The second one is permanent dipole. So if we consider this fact, this polar molecule has two dipoles. One is induced, the second one is permanent. So, and this is a non-polar molecule. The non-polar molecule has only one type of dipole, which is induced dipole. So if the induced dipole of this molecule will interact with the permanent dipole of that molecule, this will produce Diable-Induced Dipole Interaction. Interaction between permanent dipole and induced dipole. But if the induced dipole, because this one has only induced dipole, if this single induced dipole of moment of this molecule is going to interact with the induced dipole of the second polar molecule, this will generate induced dipole interaction, which is the London Dispersion Force. Make sense? So that's why the London Dispersion Force exists between all molecules, whatever they are, polar or non-polar. If you have two non-polars, this is a non-polar molecule, this is another non-polar molecule. This non-polar molecule has only one type of dipole, which is induced dipole. That's it. There is no permanent. And this other molecule has only one type of dipole, which is induced dipole. So when these two dipoles interact with each other, they're going to interact through London Dispersion Forces or induced dipole interactions. Very simple. But in case that you have polar and non-polar molecule, the polar would have two dipoles. One is induced, one is permanent. But the non-polar has only induced. So when the induced interact with the induced, this gives London Dispersion Force. With the induced dipole interact with the permanent dipole, this gives Diable-Induced Dipole Interaction. In case that we have two polar, everyone has two dipoles. This one has induced dipole and permanent dipole. This one has induced dipole and permanent dipole. When the induced dipole interact with the induced, gives London Dispersion Force. With the induced, when the induced interact with the permanent dipole, gives Diable-Induced Dipole Interaction. When the permanent dipole interact with the permanent dipole, gives Diable-Dipole Interactions. Make sense? I hope things are clear. So this is very important to acknowledge how these different types of forces are going to generate depending on the polarity and the type of the molecule itself. Make sense? The last type of interaction force is the hydrogen bonding force. Hydrogen bonding force, it is simply Diable-Dipole Interaction Force, the same one, but it is a special form of the Diable-Dipole Interaction. So what does it mean? It means that the hydrogen bonding force, it generates between two polar molecules, but it is a special form. So it is a special case of the Diable-Dipole bonding or interaction. So some people give it a name as bonding, just to acknowledge this thing. So as we said that these are interactions, to be more accurate, these are kind of interactions. But the Diable-Dipole interactions, as you can see, it is type of interaction that generates between positive and negative charge of two different molecules, which is very similar to the same idea of the ionic bond. The ionic bond generates between positive and negative charge between two atoms or even two molecules. So it is very similar to be like ionic. So that's why it is kind of strong. This type of Diable interaction, it is kind of strong that it could be counted for some materials could be used for bonding material, for building a material, and it's going to do the same action or behavior like the other bonding force, like ionic force, for example, or ionic bonding. So that's why, for example, some of the people that, or in some cases, we could given him as hydrogen bonding. So this type of force, it is strong, very high, strong force. That is, it is Diable interaction, yes, but it is stronger, very strong force that could be counted for some reason could be used for building a molecule, for building a material, and it could be counted as one of the types of the bonding forces. We can add it as a bonding force. But you should understand that this type of force, it is located as intermolecular forces, not intramolecular forces. So it is a special type of Diable interaction or Diable bonding because it is very strong. So that's why we got the name hydrogen bonding interaction. It occurs between molecules in which hydrogen, so the condition that this molecule should include hydrogen that is covalently bonded to fluorine, for example, like HF, or oxygen, or the nitrogen, like NH3. So the hydrogen, it has only one electron. It has only one electron. So for every HF or HO or HN bond, it means that you have hydrogen atom that is going to be bonded with an oxygen or fluorine or nitrogen atom, for example. So what's happened that the hydrogen atom has only one electron that is shared, will be shared with the other non-metals, which are the F or O oxygen or the nitrogen with the other atom. This makes hydrogen end bond is positively charged. So for example, like HF. So we do have one electron that will be shared with the fluorine atom. So this is gonna give this side more positive than the other side. So this will induce a permanent, will generate a permanent dipole there, that this side will be positive and the other side will be negative. So this should be the direction of the Diable moment. The same thing here, we do have two directions of this Diable moment because this is positive side, this is positive side, and we do have the negative side will be that direction. So the sum of these two moments will be summed in that direction. So this is the positive side and this is the negative side, for example. When these two molecules come to each other, they gonna form like a bond through Diable interaction. So that's why we could give it a name as Diable bonding. And the main reason of the positive or this permanent moment is that the hydrogen has one electron that will be shared through a covalent bond with the oxygen or fluorine or the nitrogen. This makes one side positive, the other side is more electron rich. So this makes the hydrogen end in the bond is positively charged and is capable to strongly attract a negative end of an adjacent molecule. Like this case, this positively charged hydrogen forms a bridge between two negatively charged atoms. For example, as you can see, this positive charge, the hydrogen atom, will work like a bridge between two negatives. Like it will be attracted, positive will be attracted to a negative from this side and another negative. Then you'd have hydrogen, which is positive, then hydrogen positive, that a bridge between negative and negative, and hydrogen between negative and negative, and so on. So as you add more atoms and more molecules, you're already forming a material. So this could give like a material. So since it's going to work like a bridge, and this type of force, interaction force, it is very strong to be counted like a bond, like a bonding force, and it's going to keep these molecules hold together all the time. So that's why it would be qualified as a bonding force. Hydrogen force is the strongest of the intermolecular forces, and the main reason because of the existence of the hydrogen. Make sense? So these are the four types, but you're gonna deal with the hydrogen bonding interaction. It works with the same concept as the Diable interaction, but the special thing of that type of force that it depends on the hydrogen atom that will be merged with F or oxygen or nitrogen or N. Make sense? So these are the different types of forces. So far, over the 3 videos, we have discussed 3 groups or different types of forces. Some forces that located inside the atom, and we do have the intramolecular forces, which are the bonding forces. In addition, we do have the intermolecular forces, which are 4 forces. So in total, we do have the intra 3 forces, ionic, covalent, and metallic bond, and we do have the intermolecular forces are 4 forces, which are induced dipole and the London Dispersion Force, and we do have the Diable or permanent dipole induced dipole, and we do have the Diable interaction and the hydrogen bonding interaction. Make sense? So this table gives a summary of the intramolecular forces and the intermolecular forces that would be generated between molecules and atoms inside the materials. Here we are not including the forces inside the atom itself. We are talking about the forces that would be generated between 2 atoms or 2 molecules or 1 atom and another molecule. Make sense? So, if you have 2 atoms, for example, they could be strongly bonded together through covalent bond. This is very strong force. So that's why it is qualified as a bonding force. It is a bonding force. And the function or this type of force depends on the distance between the 2 atoms or the 2 molecules. But this relation, it is kind of complicated for many of the material. And this type of bond, it exists for most of the ceramic material. We said that ceramics are mainly made of non-metals or metals and non-metals. So this covalent bond generated between 2 non-metals by sharing atoms. So since these atoms, they're gonna share, sharing electrons. Since the atoms, they're gonna share electrons, this will generate a very strong bond that it will be difficult to be broken unless you apply a very high energy to break this type of bond. Ionic bond, it is very strong bond that also generate between 2 opposite charges like metal and non-metal. So you're gonna generate an ionic bond that require positive and negative charge. And this type of force, it could be related to the 1/r, where r, this is the distance between the 2 atoms that form a molecule. And it would be generated between metals and non-metal atoms. Like you have metal atom and non-metal atom that would be exist in most of the ceramic material. Metallic bonds are strong, but it is not strong like the others, like the covalent and ionic bond. It is weaker than the ionic or covalent bond, and that's why it is located or used or found in many of metals, like in case that you have 2 metal atoms. But the relation between this type of force and the distance between the atoms, it is kind of complicated. It is not just like the ionic that depend on the inverse of that distance. And we do have, so these 3 are intramolecular forces. These are bonding forces. But in addition, we do have the intermolecular forces, which are the other types of forces. We do have ion dipole force. We didn't discuss this thing before. What is the ion? The ion, it is an atom. We said that the intermolecular forces could be generated between 2 molecules, or would have some type of forces that could be generated between 2 atoms, or 1 atom and molecule. We have discussed that the molecule, it could be polar or non-polar before, right? The same thing for the atom. The atom, it could be like kind of polar and non-polar. This atom, it could be like ideal atom, just atom, or it would be ion. So the ion, it is like the polar molecule. The same concept. So again, the molecules could be polar and non-polar. Atoms could be atom or ion. The ion, it is an atom that has gained or lost more, 1 or more of its electrons, and therefore it has a negative or a positive charge. So the ion, it is just an atom that carries either a positive or negative charge. This is the ion, just to understand. So it is just an atom with a certain charge. In the conventional form of the atom, it should be neutral. That has a nucleus of a positive charge, and there are lots of electrons surrounding it, right? So this atom, in the ideal case, it is neutral. But for some reason, if this atom will be in interaction with another atom, and to be bonded to another atom, this atom would require to release one of the electrons or attract another electron from the other atom, right? Through either covalent, ionic, or metallic bond. So what's happening actually in that case, that when this atom release electron, it became more positive because the number of negative charge has decreased because it released 1 electron. So it became more positive. So it becomes positive ion. It becomes positive ion. And this positive ion will carry a certain dipole moment that is permanent, like polar molecule. It works like it is a polar molecule. So the ion, you're going to deal with it like it is a polar molecule. But instead of being a polar molecule, it became like a polar atom that carries a certain charge, and that's why it will be attracted to the molecule. Make sense? Or any other molecule. So the ion, it is an atom with a certain charge. This charge, it could be positive in case that the atom releases electrons, or if the atom attracts electron, it will be more negative because it gains more negative charge by adding more electron to its orbits, so it became more negative. So it became a negative ion. So the ion simply, it is an atom with a certain charge due to the release or the gaining more electrons from the other atoms. Make sense? So in case that you do have an ion, so the ion-Dybole interaction, it is one of the type of which is very similar to Diable-Dybole interaction. But remember that the ion, it is polar molecule, like boron molecule, but it has no dipole moment. There is no moment here. The dipole moment to generate it require a molecule that should be with a shape. But the atom, we're dealing with the atom like it is a charge, just one charge like a point. So it is a little bit different concept. It means that the ion, it has no dipole moment. It is just a charge. It is just ion with a positive or negative charge, and that's it. So if you do have a polar molecule, assume that you do have a polar molecule, and there is an atom, which is ion, could be positive or negative. This atom, it works like a charge, just one point a charge. This atom, it won't gonna rotate or nothing. No, this atom, if it is positive, it will be attracted to the negative side of that molecule. Through an attraction force, this attraction force will induce Diable interaction. Make sense? If this ion is negative, so it will be attracted to the positive side of the molecule through an interaction also is known as the ion-Dybole interaction. So the ion-Dybole interaction, it works the same concept like the Diable-Dybole interaction, but you should understand that the ion, it is an atom with a charge, but the ion has no dipole moment. There is no dipole moment here. The thing that has a dipole moment is the molecule itself. So in case that you do have an ion, which is atom with a charge, that comes close to a polar molecule, this type of interaction is going to generate, and it is kind of strong. And it could be related to the inverse of the squares of R, which is the distance between the atom and the molecule. This is the relation of this, or the magnitude of that force will be dependent on the 1/r squared. The hydrogen bond, it is very strong. Here we are starting from the strongest force to the weakest force. So the hydrogen, it is a strong force that it could be weaker than the ion dipole. So we may have an atom that is attracted to a molecule. This ion dipole could be stronger even than the hydrogen bonding force. The hydrogen bonding force or interaction, it is very strong, or a strong force, like very similar to the ion dipole. It is very complicated. Its magnitude, the magnitude of that force in comparison to the distance between. We said that the hydrogen, it is generated between two polar molecules, but the condition is that these two molecules should include hydrogen atom, like HF, HO, or HN bonds should be there. And the magnitude of that force, it is very complicated in terms of the distance between these different molecules. We'd have also what comes next is Diable-Dipole Interaction. Diable-Dipole Interaction, we said that it is kind of moderate force that generates between two polar molecules. You'd have polar molecule that carries a permanent dipole, and we'd have another polar molecule that carries a permanent dipole that will generate Diable-Dipole Interaction. Ion-induced dipole. Ion-induced dipole, it means that you'd have an ion which is atom with a charge. Induced dipole, it requires nonpolar molecule. Like this type of interaction is going to generate between an atom with a charge and a nonpolar molecule. So when they collide to each other, this nonpolar molecule will induce a dipole, will generate an induced dipole. This induced dipole will be interacting with the charge within that ion to generate an ion-induced dipole interaction, which kind of weak force in comparison to the other forces. That's why it is related, its magnitude depends on the 1 over r power 4. So as you can see, as we increase the exponent or the power of the r, which is the distance between the ion and the nonpolar, or the two objects, the magnitude of that force is going to decrease. We do have next Diable-induced dipole interaction. Diable-induced dipole generate between a molecule with a permanent dipole and a nonpolar molecule that is symmetric. So this generate between polar and nonpolar molecule, and it is very weak force that of a magnitude equal to the 1 over r power to 6. London Dispersion Force, this is the weakest of them all, that included, that found in all molecules. This is something that you should understand, that this London Dispersion Force is generated between all molecules, wherever they are, even between atoms themselves. It exists. So this is the forever force that exists between all molecules, no matter what they are, polar or non-polar. But how could we understand how it works? You should assume that you do have two nonpolar molecules to understand how it works, as we explained before. Make sense? So these are the different types of forces that we have discussed over these slides. The last thing that we need to discuss here is the London Dispersion Force, or in other words, how we could calculate the van der Waals energy. So, as we mentioned, London Dispersion Forces, dispersion forces are always exist between all molecules and atoms, no matter what they are, ions like atoms, or non-ions like just conventional atoms, or polar or non-polar molecules. So they do exist between all of these forces, between all of these objects. Dispersion forces may be attraction or repulsion forces, or repulsive force between two atoms or molecules. So, how this London Dispersion Force, or in general, if we're going to talk about these intermolecular forces, all of these intermolecular forces, all of these different types of forces, their tendency is non-bonding force. So what does it mean, non-bonding force? It means that the two objects, like two molecules, when they're going to come together, this force is going to generate, for some reason, if these two molecules are moved apart, so the magnitude of that force should be 0. You got my point? So it means that this type of force, all of these different types of forces, I'm talking about these forces, not the covalent or ionic or metallic. These are bonding forces, so they're gonna be there all the time, holding the objects together. But here I'm talking about the interaction. Interaction, it means that this type of force, it is non-bonding force, that it would be generated or degenerated depending on the distance between these two objects, like two atoms or molecules. So the dispersion force, it could be attraction or repulsive. Attraction, if these two molecules are apart from each other at a certain distance, but when they're gonna come very close to each other, this force will be repulsive force. And this explains the repelling of the electrons that is happening when the two molecules are colliding together in the London Dispersion Force, as we explained before. So there should be some repulsive force upon coming very close to each other. This is what makes the electrons are repelled, right? So the dispersion force depends on the separation or the distance between two atoms or two molecules, which we're gonna give it a symbol as R. Like assume that you have one atom here and there is another atom and the distance between them is R. So if we decided to draw a schematic or draw the function of that force, how it do depend on the distance R, this London Dispersion Force, this force, it will be, as you can see, as we increasing R here it is very high distance, so in the magnitude of that force almost 0. It comes exponentially decaying and decreasing as the distance R increasing to be almost 0 as at very high value of R. But as R decreases, as we decrease the distance between, it means that these two atoms or molecules come close to each other. They are coming close to each other. So the magnitude of that force will continue to increase. Just follow the rate curve. Going to increase to be maximum at a certain value. Then beyond that maximum, they're gonna start to decrease to 0 again at a certain distance R. then they're gonna switch from being attraction force to be repulsive force. Remember that the repulsion force, it should be negative, going down. It means that it is repulsive force, and it's gonna be attraction force in case that it is positive. It means that if it is on the upper side of that curve. So this is basically, this is how it works. If you do have two atoms and they're gonna be attracted through London dispersion forces, these two atoms at a certain distance, the magnitude of that force will be weak. As long as very small, it will be almost zero, as long as these two atoms are very apart from each other. But when they're gonna come close to each other, the magnitude of the forces start to increase, but it's attractive. Attractive, it means that these two molecules are attracted to each other. They're gonna be keeping attraction and coming closer at a certain distance. This attraction force will be switched to be repulsive. When they're gonna come very close to each other, this force will be repulsive, pushing these electrons back again. So these two electrons will be pushed back again and separated apart till the magnitude of the force, it will be changed again to be attraction. So they're gonna come close to each other and continuously moving in that way. Okay, you can understand it in this way. So this is the basic idea of this dispersion forces, and the same for any other dispersion force, whatever it is, Diable-Dipole interaction or Diable-Induced interaction or the induced Dipole interaction like the London dispersion force. Make sense? So that's why we do have two sides of that force, two faces or two types of that force. We do have attraction side and we do have the repulsion side of that force. So the net force, actually, it could be expressed between two atoms, can be decomposed into attraction force and repulsive force or repulsion force. So that's why we're gonna say that the total force of London dispersion between two molecules or two atoms, it is the sum of attraction part of that force plus the repulsive part of that force. When they're gonna combine together, they're gonna give us the red curve as represented here. Make sense? Since we are talking about a force, there should be an energy. The force, it is kind of energy, because this force, it tend to move. If you multiply the force times distance, gives the work, which is a form of an energy, right? So it means that the force, it is related kind of to the energy. This type of energy is known as the potential energy. So what does it mean, potential energy? It means that these two atoms, they do have the potential to move. They do have the potential to generate some forces between them. This potential, it can be expressed as potential energy, which we would give it a name as E, stands for energy. So this is the potential energy between these two molecules. This potential energy, it is type of embedded internal energy that would exist between any molecule that form any material. So that's why we do have the materials, they do have their own energy, internal energy that embedded and saved inside this material. Like one of these energies, for example, is the intermolecular forces that generate between the molecules of that material. Make sense? This potential energy, any energy to be calculated from the force, if you just integrate the force over the distance, this is gonna give us energy. Right? This is what we knew from physics or mathematics. So the integration of the net force over dr, which is the change. Dr stands for the change in the distance between the two molecules. This is gonna give us, if we substitute with this relation, Fa plus Fr, which A stands for attraction, R stands for repulsion. So this is gonna give us the integration of Fa dr plus the integration of Fr dr. This is gonna give us one term, which will be attraction energy, and another term which will be repulsive energy. So as you can see, this is the curve for the energy, but this is the curve of the force that we explained. Again, as we increasing the distance between R, the magnitude of this potential energy become very close, very small, decreasing. It decreases as the R, the separation between the two molecules or the separation distance between the two atoms or molecule is increasing. The magnitude of this potential energy is going to decrease. And it's going to increase as the distance R is decreasing, is going to increase the magnitude. Here I'm talking about the magnitude, forget about the signs, just the magnitude, the value of that energy will be increasing as R decreases to be maximum, then it's going to decrease again to zero to be switched to the other side. And again, the energy could be positive and negative, but as you can see, the energy has an opposite sign to the force. Why? Because of the integration. If you integrate or differentiate any function with a variable that located in the denominator, this will result in a negative sign. And if you remember over this table, we said that the magnitude of all of these forces depends on the inverse of r, which is the distance. So here we are doing the integration with respect to r, right? And this r is located in the denominator of this function. It means that this will result in a negative sign. So that's explained. This is what explained that in case that you do have the potential energy is positive, a positive potential energy between these two molecules indicate a repulsive force. But the negative potential energy between two molecules indicates an attraction force. Make sense? So that's why the positive of the force will be negative for the energy, and the opposite side, the vice versa for the repulsive or the attraction. Make sense? So in generally speaking, we said that the London dispersion force, it depends on the distance between the two molecules, and since there is a force, definitely there is an energy. And the magnitude of this force or energy depends on the distance between these two molecules. And the magnitude of this force or energy, it could be repulsive or attractive depending on the distance between them. Very close to each other, this force and energy will be repulsive energy and force. At a certain distance, a quite good distance between them, this force or energy will be attractive force and energy. And this is what we would like to demonstrate over that point. Make sense? Alright, so here we're just talking about one type of dispersion force, one type of force of interaction between these two molecules. This is in case that these two molecules are non-polar. How about if these two molecules are polar molecules? We said that there is three types of forces that is going to generate between two polar molecules. One is Diable-Dibole, that depend on the interaction of the permanent dipoles of these two molecules, and induced Dipole, and induced Dipole. So three forces that is going to generate here, right? The London dispersion force definitely is one of them because it exists between all molecules. So how about if we do have two polar molecules? So definitely we should have three types of energies. So this is the function of just one interaction. This is the energy, the potential energy due to one type of interaction. If we do have two polar molecules, definitely we're going to have three types of interaction. It means that we do have three types of energies. We do have energy that depend on the Dipole-Dipole interaction because these two molecules are polar molecule. So we do have Diable-Dipole interaction. It means that we do have Diable-Dipole energy. Also, we do have Dipole-Induced Dipole. So that's why we would have D stands for Diable, I stands for Induced Dipole interaction energy. We do have the dispersion, which is London dispersion, which is induced dipole interaction. So that's why the sum of these energies is known as the van der Waals energy or van der Waals attraction force, or force for now. So the van der Waals force, it is the sum of the three interactions that could be generated between any two molecules. In case that we do have two polar molecules, how many terms that the van der Waals force or energy should have? It will have three terms. One term is due to Diable-Dipole interaction, the second term due to Diable-Induced interaction, the third term due to dispersion. But how about if we do have two non-polar molecule, so the van der Waals energy will be only one term, which is the energy dispersion. This term will be zero, this term will be zero. Why these terms are zeros? Because there is no polarity here. We have only induced dipoles. It means that this the only term that we have. In case that we do have polar and non-polar molecule, so we're going to have these two terms only. We're going to have Dipole-Induced Dipole interaction, and we're going to have the dispersion that exists between all molecules. But this term will be eliminated. But in case that we have two polars, so we're going to have the three. Make sense? So the EV stands for van der Waals energy is the total van der Waals potential energy. EDD stands for the Diable-Dipole interaction or ion-dipole interaction in case that you have ion and molecule. interaction. The Dybol, the EDI stands for the Dipole-Induced Dipole Interaction, and the dispersion stands for the London Dispersion Interaction energy. So the sum of these energies give the total van der Waals energy. So the van der Waals energy, it is not one of the types of the interaction forces or the interaction potential. It is the sum of all the potential that could be generated between two molecules, depending on their polarity, whatever they are, polar or non-polar. Make sense? For example, how we could calculate, there is some expression, multiple expressions. Usually the sum of these interactions is very weak in comparison to the bonding force, and many of the cases they are related to the inverse of the R power to 6 or a certain number depending on the magnitude of the force. So we could express this London dispersion or van der Waals force or energy as the negative of CDD, stands for the Diable and Diable induced and dispersion, and this C is known as the energy coefficient. It is constant that depends on the material type, and R, this is the distance between the molecules that form that material. All right, so at this distance increasing, the magnitude of this energy will be decreasing. As this distance is decreasing, the magnitude of this energy will be increasing. And this negative sign here is included to indicate that this is attraction force. So that's why here we are talking about the attraction force. It means that these two molecules will be attracted. So that's why we are incorporating this negative sign here. But remember that this energy, it should have two sides. Like one is attraction, the other one is repulsive force or repulsive energy. So these C's are the energy coefficients of Diable-Induced Dipole and dispersion interaction respectively. So the force, if this is the energy function, to find the force from the energy, if you just differentiate the energy function with respect to R, which is this R, this is gonna give us this relation. And that's why, as you can see, this one will be positive as long as this one is negative. All the time the energy and the force, they do have two opposite signs. This is what we knew from the derivative of something that, of a variable that located in the denominator from the mathematics. Make sense? But as I said, that this is how we could write or express the van der Waals energy or force in case that it is just attractive. So if we could let us collect these three C's in one variable as P, and let us say that this B, it is like a material parameter that distinguish one material from another material that depends on the material type. So we're gonna say that the E is gonna be the negative of B over R power 6. The same thing could be happening here. We could collect these C's together into just B. But as I mentioned before, that this potential energy, it has two sides, two types. It would be attraction or repulsive. This is in case that there is attraction energy. In case that it is repulsive, if we decided to add the two types of forces or energies together, the attraction and the repulsive in one term, so this is gonna give us pair potential. Here we are talking about the pair potential energy. So pair, it means that these are the two pairs. These are the two sides of this energy. But one pair or one side, it could be like attraction energy. This is just the attraction energy. If you needed it repulsive energy, this sign will be positive, and the magnitudes of these coefficients will be different for the repulsive side. So this is just one type of this energy, one form of this energy. But in general, it should be repulsion and it should be attraction in the meanwhile. So there are two sides, repulsive and attractive energies. The repulsive, it should be positive, and the attractive energy should be negative. So that's why we do have a negative side here. If we added both of them together, this is gonna give us the total intermolecular pair potential. Here we are talking about the pair as positive plus the negative, or the repulsive plus the attractive. Make sense? Is obtained by summing the attractive and the repulsive potentials together, as already shown here. So this B stands for the magnitude of the C plus the C plus the C. The C Diable, the energy coefficient of Diable interaction, Diable-induced interaction, or the dispersion. We sum these constants together in one B, which is a material property. We can do the same for the attraction. So we do have different C's, but for the attraction side, which we could combine all of these C's for the attraction, for the repulsive, to be A. So the magnitude of the C's, or the energy coefficients of all the total interaction for the repulsion, we give it a symbol as A as a material parameter, and B is another material parameter referred to the C's, or this energy coefficient for the attraction side. Make sense? And in general, even the attraction, it could be related to the to a power that is different than the repulsive. It means that the repulsive, it could be power to 6 or 7 or 8, a different number. So to give it a general form, this is the very general form of the intermolecular forces as bare potential energy that would be generated between any two molecules, no matter what they are, what is the type of these two molecules. That is, generally it will be A over R power n, and it would be any integer, constant value, negative B over R power to m, where all the time n, it should be bigger than m. These are two exponents, two constant integer values, like for example 8 and 6, 9 and 12. So this depends on the material type. So three things here. This energy, it is a material property. And this is the main objective of this course, is to try to understand how the material properties are related to what's going on inside the material structure. Here we start from the atomic interactions. We discuss the different forces, how these forces would influence the material properties. This is happening here through this relation. This relation relates the material property to the different types of forces that could be generated inside this material. We may have a material that is made of polar molecules. So this A and B, N and M will be with a certain value. If we have another material that is made of two nonpolar molecules, this A, B, N and M will be of different values. So these four constants are material properties that are different from one material to the other one. Make sense? This A and B is known as the coefficient energy, the energy coefficients, which are like the C's, but you should understand that this B and A are the sum of the C's of the different forms and types of interactions between the molecules. Make sense? A very common form that many of the chemistry engineers who are using molecular dynamic simulations and other things are using is the Lennard-Jones potential, which is this form. The Lennard-Jones potential, it is for epsilon. Epsilon, this is known as the energy constant, which has the unit as joule per mole, for example, as unit, the unit of the energy. And this sigma, it is a distance that depends on the distance between. It is a constant, like with a unit or dimension of a length, like the r, which is the distance between these two molecules. The sigma also depends on the radius of this molecule and the radius of that molecule in many of the cases. So we are using, if you just compare this thing or this expression to the previous one, you're going to find that N will be 12 and M will be 6. So that's why N, it should be bigger than M. This Lennard-Jones potential is very common, that many of molecules that form most of the material that we are using or dealing with as engineers are the type or the sum of intermolecular interaction between them can be perfectly modeled by the Lennard-Jones potential with that form. So that's why this Lennard-Jones potential, it is very common. So something that you should understand here, that this type of potential, it should sum all the intermolecular interaction that would be exist between the molecule that form that material. And this depends on the type of the molecule itself. Is it polar or not polar? And the types of the dipole moments that could be generated, whether it is permanent or induced dipole moments. Make sense? So that's it for this video and this part on chapter 2. So we have finished chapter 2. Again, chapter 2 just to discuss the things that happening at the atomic scale. The type of interaction forces that would be located, or forces located inside the atom or outside the atom. We discussed three groups of forces. The forces found inside the atom, and two groups are found outside the atom, which are the bonding forces and the intermolecular forces. Through this third video, we have discussed the intermolecular forces. We discussed the induced, which commonly known as the London Dispersion Force, and the Diable-Induced Dipole Interaction, and we discussed the Diable Interaction and the hydrogen bonding, and then we discussed how we could form the energy potential for these different types of intermolecular forces. These things are very important since we are working in material science to understand them and how these forces would be related to the material properties and influence the material properties. This is what we discussed over these 3 videos, right? So that's it for chapter 2. And again, this had been covered over 3 videos. This was the 3rd one of them. So that's it for today. And thank you so much, and see you in the next meeting. And we're gonna start new chapter, which is chapter 3. Thank you.